2.8 and 2.9 key points. The purpose of this video is just that we are going to be skipping sections 2.8 and 2.9 for now. We're going to come back at them later in the course, but there is some key vocabulary that you need to be familiar with, so we're just going to hit them quickly right now, and we'll be talking a lot more about them in chapter 3. So some notations for derivatives that we've already seen is f prime of x or y prime. We've also seen dy dx, meaning the derivative of y with respect to x. We can also denote it as df dx and d dx of f of x. We won't be seeing these last two in this course at all. The Leibniz symbol dy dx, we need to be careful. That's not actually a ratio. It's just another way of saying f prime of x. We do not want to read dy dx as dy over dx. It's dy dx. We can also say dy dx is the limit as delta x approaches 0 of delta y over delta x. Just the limit as delta x approaches 0 of the slope. Delta y over delta x is just the slope. And so that's just saying, let's take 2 points, get them really, really close together, meaning let the gap between the two get close to 0. In other words, let delta x approach 0. If we want to find f prime of a, the derivative at a particular value a, then we would say, let's evaluate dy dx at x equals a. So this bar means let's evaluate it at x equals a. And we can also use a bracket. Differentiability will be a key term. A function is differentiable at a if f prime of a exists. We can also have differentiability over an interval. We're going to look at some pictures in upcoming slides, which is going to make this make a lot more sense. But for now, let's just keep in mind that the derivative must exist at all points a in order for the function to be differentiable. Really important connection is between differentiability and continuity. If a function is differentiable, then it must be continuous. If it fails to be continuous, then it can't possibly have a derivative at each and every point. However, the converse is false, meaning if it is continuous, we do not necessarily know that it's differentiable. It may or may not be. A prime example of that is just the absolute value function. We know the absolute value function is continuous everywhere. We can draw that function without picking up our pencil. However, it's not differentiable at x equals 0. We cannot find the slope at that point. And now let's take a look at a picture to make this clearer. The first example, we have a corner at A. That's right here. And what we're saying is, if we look at from the left-hand side at the tangent line, it's positive. And then we go a little bit further and it is a huge jump. So at x equals a, we have this huge jump. That is an example of failure of differentiability. In number 2, that's just our easiest example. If it's discontinuous, then it can't be differentiable. And number 3 is just the case of a vertical tangent, where at A, we actually have an undefined tangent line. The second derivative is just denoted as f prime prime. In other words, let's take the derivative of the derivative. In Leibniz notation, we'll say let's take the derivative d dx of the derivative dy dx. And we'll get very familiar with this notation as we go on in the course. Now, I know it doesn't look so familiar, but it will. We can interpret f prime prime as the rate of change of the rate of change, right? Because f prime is just a rate of change, and so its derivative is the rate of change of the rate of change. In other words, the rate of change of the slope of the original function. If we're talking in terms of a physics application, we know that s of t is the position function. We've talked about its first derivative being the velocity, and the second derivative is just going to be the acceleration. The acceleration is the rate of change of the velocity function. higher order derivatives as we go on. We don't really want to write f prime, 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 prime. So instead of that, we will denote it like that. Now let's kind of go backwards here. Let's see what f prime says about our actual function. So if our derivative is positive, that means that our tangent lines all have positive slopes. In other words, the function is increasing. We see from B to C that our function begins decreasing, and so it would make sense that the tangent lines are all negative. So if f prime is negative, then we can say that the function is decreasing. Don't get confused with negative and decreasing. We want to say if our derivative is negative, then our function is decreasing. We're going to talk a lot more about that. From C to D, we again see that f prime is positive, so the function is increasing over that interval. Concavity, I like to think of concavity as our happy functions and our unhappy functions, so you will hear me referencing a happy function as a concave up function. It's feeling happy, it's feeling up, it's feeling concave up. So another way of saying this is if f double prime is greater than 0, then we have a concave up function. Our function is concave up. What does that mean? That means that the rate of change is positive. In other words, the tangent lines are getting bigger. Now you might note that our first tangent line drawn here is negative. True, but it's getting less and less negative as our x values get greater, and we see that it actually becomes quite positive at the end. Vice versa for concave down, f double prime is negative, and we see here that the tangent line actually begins positive, but it's becoming less and less positive, and then it does become negative. So here was our key definition, concavity. And then we have an inflection point. An inflection point is just where a curve changes its direction of concavity. So it changes from concave up to concave down or vice versa. So just a quick little picture would be like this. We see our function is happy here and it's unhappy here. And where does it change from being happy to unhappy? Right there at that point. So that is defined as our inflection point. Antiderivatives are just a way of going backwards. So instead of finding the derivative, we might want to find its antiderivative, so we go backwards. If we have a function f, then we denote its antiderivative as capital F. And the derivative of the antiderivative is just going to be the function itself. So that's it for the key points from 2.8 and 2.9. And remember, we will be hitting them again later on in the course. We just need this as our basic vocabulary going into Chapter 3.